The ocean wave. From our harbor of Port Electron, we want to chart a course towards the coast we see finally on the horizon. The local pilot we have engaged is impatient to steer us out of the harbor through the calm of the bay and around the patches of the choppy water we can see by the harbor's entrance. But our navigator and the captain are cautious. The conscious of the challenges ahead, that they want to understand what caused the choppiness. What's that? And how to steer the boat safely themselves. The pilot shrugs and they start talking about particles. Particle-like behavior is something we are quite familiar with. If you shoot a gun, the bullet will travel outward in a straight line until some force acts to change its direction or slow it down. So there must be some acceleration as an element of the force, right? Sand will trickle through your fingers and form neat piles. These particle-like things will not travel in anything other than a straight line unless they ricochet off to something or some other forces act on them to bend their path. They will also stay the same shape as they travel. To properly describe a particle and predict its behavior, we need to know its size, speed, and mass. We think of the molecule in the gas as a particle, bouncing off each other, and with that picture, we can understand the temperature, pressure, and quite an array of interesting and useful behavior, including convention currents that transfer heat energy around the cabin. Particles also provide a way of transferring information. The letters the crew sent home before we set off on our journey are particles too. In a sense, the discrete packets of the stuff traveling in a well-defined path from the sender to recipient. Waves provide a very different way of transferring information and energy. The ship's radio, emergency use only, sends the signals back to the base, and the ship's microwave heats up the captain's soup. Most of what we know about the world around us comes from the waves, generally light waves and sound waves in everyday life, but also radio, X-rays, and more esoteric form once we bring scientific instruments into play. The physics of the wave is in many ways more interesting and more complex than the physics of the particle, and gives rise to a richer mix of the effect, including the choppy and calm patches the captain saw as we arrived. Because the sine function, sine wave itself has a mathematical expression, right? To properly describe a wave, we must know its wavelength, frequency, and amplitude, right? Traveling waves have peaks and troughs that moves as they go. But what is actually traveling? The pilot draws our attention to the seagull sitting on the water of the bay as ripples in the otherwise calm sea pass by and lap at the shoreline. The gull bobs up and down as the wave passes, but does not otherwise move. Tough waves are traveling across the bay to the shore. The seagull and indeed the water through which the waves are transmitted only move up and down. They do not travel along the surface. It is only the up and down motion, the displacement, which is somehow traveling across the bay. The height of the up or the depth of the down compared to the surface of the undisturbed bay is what is called the amplitude of the wave. Any wave has an amplitude of some kind. Yes, physics! The displacement that is caused from the average. An amplifier in a sound system is so-called because it increases the amplitude of the wave. It amplifies it and the sound gets louder. As the ripples continue, perhaps the dolphins is having a good time nearby, splashing around. The girl will keep on bobbing up and down. The number of times it bobs in the given period of time is known as the frequency of the wave. Sure. The frequency of the wave, the number of peaks or troughs passing a given point in a certain time interval. Usually it is measured in hertz, Hz, a slightly odd unit which should really be called per second. Yes, per second. If the wave in the bay has a frequency of 2 hertz, the girl will bob up and down twice every second. Haha. The wavelength, on the other hand, is simply the distance between the two neighboring peaks in the series of the ripples. And since the displacement has to travel a distance of the one wavelength each time the girl bobs, the speed with which the wave travels across the pond is quite easily calculated by multiplying the frequency with the wavelength. Yes. So, if we know the amplitude, the wavelength and frequency of the wave, we also know its speed and specifies all of its most important properties. Wow. So if we know the amplitude, the wavelength and the frequency of the wave, we also know its speed and that specify all of its most important properties. How is the behavior of the waves any more interesting in any sense than the way particles behave? Well, consider this. 2 dolphins are splashing around in different places in the bay, making waves with the same amplitude, frequency, and wavelength as each other, but traveling in different directions. Things might be looking a bit turbulent for the girl, but perhaps not. Yeah? If the peaks of the 2 waves arrive at the seagull at the same time, then indeed the bird is in for a bumpy ride. The amplitude of the wave will add up, and the girl will bob twice as high and dip twice as low. Wow. Yes. Depending on how far away each dolphin is from the girl, it might be the case that the peak of one wave arrives just as a trough of the wave from the other dolphin turns up. In this case, the trough will cancel out the peak, or thinking of it in terms of the water under the seagull. The force from one wave is telling it to move up, while the equal and opposite force from the other wave is telling it to move down. It won't move. The girl can relax. The wave will carry on past it, but it will be left in space. Such quiet spots are seen when all kinds of waves meet each other. Radio waves and microwaves, such as those which carry Wi-Fi signals, exhibit them too. Wow! These effects, when waves come together, are known collectively as interference. When 2 waves arrive with the peaks of the one hitting the trough of another, they are said to be out of phase. And obviously, when the peaks come together, they are in phase. Phase is another important property of the waves, but it can only really be defined when you have 2 waves. Phase differences, such as whether the 2 waves are in or out of the phase, have a real physical effect. In our example, the gulk bobs up and down or does not, depending upon the relative phase of the 2 waves. Yes. But phase has to be defined relative to something. If there is only one wave, we might decide to define the phase relative to some arbitrary time, say the moment we first saw the dolphin. But regardless, if there is only a single dolphin making a single set of the wave, the girl will bob up and down whether the phase of the wave might be. It is only when you have multiple waves with phase differences between them that we see really different behavior. This rather simple fact has a surprisingly far-reaching consequences. This interference behavior is very different from the more familiar behavior of particles. While the bullets fired at a seagull from the different directions may collide, there is no way that firing more shoot could reduce the number of the bullets, but making more waves might indeed make its part of the bay calmer. Waves do their interesting. Waves do other interesting, non-particle-like things. The bay contains a harbor connected by the narrow channel. All the dolphin and seagull action is happening in the bay, and some of the waves impinge on the narrow channel leading to the harbor. What happens? If waves behave like a particle, then any that were directed accurately enough at the channel would pass through and travel in a straight line across the harbor, leaving most of the surface of the harbor undisturbed. Yes. But this is not what happens. The wave hit the channel, and the channel acts as the source of the wave in the harbor, as though the dolphin had actually got in there. This works mostly effectively if the width of the channel is comparable to the wavelengths of the waves, as in the case it looks like the single source of the wave rather than a row of sources. Waves will spread out from the channel concentrically across the dolphin-free harbor. This spreading out is called deflection. Yes. It allows wave to go around corners without any bending force being applied. So there is without any bending force, or in other words, acceleration. In other words, the mass times meter per acceleration. It's another key property which features in the quantum particle wave world of the standard model. One important practical consequence of this kind of the wave behavior is that there is a limit to the smallest structure they can be used to study. Roughly speaking, effects such as diffraction and interference mean that the wave cannot give us good information about objects which are smaller than the wavelengths of the wave. Smaller than that, and the things become too blurred and confused. In the case of the harbor channel above, wavelengths much shorter than the width of the channel leads to tight beam pointing back to the position of the channel. Wavelengths the same size as the channel spread out and fill the harbor. Longer wavelengths will not even pass through the gap. Any setup which can support a wave has an equation behind it. Okay? A wave equation. Yeah, of course. Which describes how the wave will work. The surface of the bay we are sailing on is one such system. Another example is the air. A small region of dense, high-pressure air will spread out, compressing the neighboring regions, which is in turn compress their neighbors, and so on. A high-pressure pulse propagating through the air like this is a sound wave created when air is compressed somehow, say by a vibrating drum or your larynx. Electric and magnetic fields from the another system, which is how light, radio, and other electromagnetic wave travel. Electric and magnetic fields form another system, which is how light, radio, and other electromagnetic wave travel. The important point here is that the general behavior of this system is similar in some way, very important way, including the fact that diffraction and interference occur because the underlying wave equations are very similar. Because they will be such a vital navigational aid in our coming voyages, it might be worth taking a moment to examine why the equations are so important in physics. We will not need to go into the detail of mathematics, and I will not be writing out any equation explicitly, but there will be several moments when an equation of some kind is so vital to navigating the physical world that we will need to discuss it. As the equation in the mathematics relates different concepts to each other in an abstract but completely definite way. When used in the physics, the concept on each side of the equation are physical objects, and an equation relating them gives new insight into how those objects behave, and especially how changing one of them affects the others. In the current case, a wave equation describes the changes in some physical quantity: the height of the water, the pressure of the air, the strength of the electric field. Wow! It relates how they change as time passes to how they change with position. Specifically, the wave equation for our bay tells us that if the height of the surface is different at the different points in the bay, this implies that the surface will also change with time. Imagine a wiggle from the tail of one of our dolphins that raises a region of the water to be higher than its surroundings. This is an unstable situation. The small hill of the water created by the dolphin will be pulled down by gravity, and this will spread the ripple across the surface as a traveling wave. The wave equation is simply the mathematical description of how this happens. It tells us how differences in the height of the water at different places lead to change in the height at different times. It can be used to predict how waves will travel and interact: water waves, sound waves, radio waves, or quantum waves. Our boat heads out of the harbor in a straight, particle-like line. The crew, cheered by our pilot's instruction and buoyed by the waves. We now know and hopefully understand two distinct behaviors: particle-like and wave-like. Yes. They differ from each other profoundly, and it is very hard to see how the two could ever be mixed together. But we are sailing an uncharted and dangerous sea, and we should expect surprises and to the frustration of some of the more impatient new members. Our pilot is not done yet. Ha ha ha.